So this is the last topic in chapter 9, and this is bond enthalpy, which is defined as the enthalpy change required to break a particular bond in 1 mole of gaseous molecules. And something's not working here. There we go. I'm going to go ahead and bring all of these in. Here are some bond enthalpies for some diatomic molecules or binary molecules. Pull that in too. H2Cl2, here we're breaking one single bond in both of these molecules. HCl, we're breaking an H to Cl molecule, or bond. This is a covalent molecule. Of course, the others are too. O2, let me point out, these two have single bonds. And you'll note that it requires more energy to break that H2 bond, or hydrogen-hydrogen bond, because they are much closer together in space than the chlorine molecules, or chlorine atoms, sorry about that, because they're bigger. And again, here we have that binary molecule to different atoms or elements in that. Then we see a double bond and a triple bond. You'll see that the energy required to break that triple bond in nitrogen is much greater than the energy required to break the double bond in an O2 molecule. So single bond enthalpies are smaller than double bond, which is smaller than triple bond. So basically, bond enthalpy is a measure of the stability of a molecule. Bond energy for breaking a bond is positive, and bond energy for forming a bond is negative. So the breaking of bonds is endothermic, forming of bonds is exothermic. This is a table of average bond energies. You can, for diatomic or polyatomic molecules, something you can look up, as you'll note that there are a number of types of bonds listed here, and you will always be provided with those enthalpies if you need them for a problem. Water, the delta H for breaking water into hydrogen ions and hydroxide ions is endothermic, a positive delta H of 502 kilojoules versus OH broken down to H and O, 427 kilojoules. So we can average that enthalpy to come up with 464 kilojoules for the breakdown of that molecule. So bond enthalpies can also be calculated directly using a formula similar to the one that we've used with calculating delta H's before. And this is the total energy input, so minus the total energy release. So what's different is calculating delta H based on bond energies versus delta H's based on heats of formation is that we are summing the bond energies of the reactants and subtracting from that the bond energies of the products. So we're going to take a look at calculating the bond energy for the formation of 2 moles of HCl. And here in this slide, we just see a cartoon or a model picture of the reactants going to products for this particular reaction. And we end up with, oh, something happened to, there we go. We're going to look at 2 actually. Making HCl and making water from their composite elements. Sorry about that. And I'm going to walk through these with you rather than show you the subsequent slides. So we're first going to look at H2 plus, and again, these are gaseous, Cl2 gaseous going to 2HCl gaseous. Okay, so I set up a table and it consists of the type of bond breaking, first of all, then the number of bonds breaking, the bond enthalpies, and I'm just going to abbreviate that as BE, and those are in kilojoules per mole, for that matter. And then we will get a delta H for those bonds breaking in kilojoules per mole, which is going to be the sum of the bonds breaking in the reactants. So we have an HH bond that's going to break. We have only 1 mole of those bonds, or one of those molecules, so 1 bond breaking. The bond energy for breaking 1 mole of those bonds is 436.4 kilojoules. We also need to break a Cl-Cl bond, of which, again, there's only 1, and that energy is, bond energy is 242.7. And then we're going to sum these. So we have 436.4 plus 242.7 to give us a total bond energy for breaking bonds of 679.1 kilojoules per mole. Now we're going to look at the type of bond or bonds forming. And that is our HCl. And so the bonds forming are H single bond Cl. We have 2 moles of HCl, so our value, whoops, something happened to my pen. So here our number is 2. I look up the bond energy for this bond forming, or the bond enthalpy for this, and it is 431.9 kilojoules per mole. I need to multiply this value by 2, and this will be the only number I need here, and that is 863.8 kilojoules per mole. Now I'm going to sum these, add them together. Well, I'm not going to sum them. Sorry about that. Let's take a step back. The delta H, I'm going to subtract them actually. Based on bond energies, is the sum of the bond energies of the reactants minus the sum of the bond energies of the products, which again is different from the way we calculate delta H using heats of formation. This is the sum of the heats of formation of the products minus the sum of the heats of formation reactants. Okay, so I subtract that, and my bond, or my delta H for this reaction is then negative, whoops, keep losing my pen, negative 184.7 kilojoules per mole. An exothermic process. Now we're going to look at the formation of water, or the delta H of water, when it's made from its constituent elements, hydrogen and oxygen, which, remember, are diatomic molecules. So we will produce 2 moles of water, and all in their gaseous states. Same process. We're going to indicate the type of bond breaking, the number of bonds breaking, the delta H for breaking one of those bonds, or a mole of those bonds, and then we will, whoops, sorry about that, let me erase that. I meant that for it to be the bond enthalpy. Then we'll come up with the delta H for the reactant, reactants. So we've got an HH, H bond, O, double bond O, and then for the water molecule, I draw the Lewis structure. I have 2 OH bonds in 1 mole of water. So H bond, and I have 2 of them because I have 2 moles, and I looked up the bond enthalpy for that bond, which is 436, sorry about that. Oh, wait a minute, no, it's 498, I was right, 498.4. I have 2 of those, so I have to multiply that by 2, and unfortunately I didn't do that in my notes, so we'll just be summing all these enthalpies together. Again, I have an O, double bond O. Okay, I went and grabbed my calculator. I've obviously made some marks here that don't belong. So I did go ahead and multiply that. This is 996.8 kilojoules. For the O2, we only have 1 mole of those bonds. And the bond enthalpy for that, breaking that double bond, is 498.7. Well, heck, I did have the wrong number there. All right. Goodness gracious. This is 436.4. Sorry about that. So this is 872.8. We only have one of these. 498.7. So when we sum these, we get 679.1 kilojoules per mole. Now we're going to take a look at the bonds forming. Now we have OH bonds, and we have 2 of those in 1 mole of HCl, or H2O. Sorry, bear with me here. But since we have 2 moles, that means we have 4 of these guys. So our bonds forming are OH bonds, again, of which we have 4. The bond enthalpy for that bond is 460. Multiply that by 4, and it is 1840.0. So we are going to subtract this value from our 679. I'll go ahead and rewrite this down here. I keep looking at the wrong thing in my notes. I should have seen that was not correct. Sorry. This is 1371.5 kilojoules per mole. So our delta H here for this reaction is the 1371.5 minus the 1840, and that gives us 468.5, and that's a negative kilojoules per mole. An exothermic process. And I think that wraps up. I added a couple other slides here. Actually, let's just do one more. We'll do H2 gaseous plus F2 gaseous, giving us 2HF, also in the gaseous state. Again, the standard heat of this reaction is going to be the sum of the bond energies of the reactants minus the sum of the bond energies of the products. If it's helpful, and with these it may not be necessary, but it sometimes is helpful to go ahead and draw those Lewis structures. You don't have to put on the electrons in if you don't want to, but just so you can see what type of bonds are present. Guess my battery is running low, so I'm going to quicken this up. Breaking number, bond enthalpy, delta H. And we have H bonds, F bonds. 1 mole of each. The corresponding bond enthalpies. And the sum of these is 593.3 kilojoules per mole. We'll take a look at the forming. These are HF bonds. We have 2 moles. Bond enthalpy is 568.2. And again, we have to multiply that. So this is 1136.4. So the delta H of this reaction is 593.3 minus 1136.4, which gives us a negative 543.1 kilojoules. And that's it for Chapter 9. I'll be making Chapter 10 videos, and we'll actually refer back to Chapter 9 with respect to the Lewis structures as we look at geometry.